All right, listen up everyone. Welcome to the Control Tower. I am your Exam Tower Director, and right now our radar grid is absolutely lighting up. We have an incoming heavy aircraft on the scope. It's a high tear of past paper questions straight from Cambridge 979 Mathematics. The exact target? Section 3.9, Complex Numbers. Now, you might think you know this aircraft. You might think, oh, it's just addition, subtraction, multiplication, and division, I've got this. But let me tell you, the exact difference between a B grade and an A-star grade comes down to one highly specific battleground: how well you truly understand the structural integrity of this topic under extreme, high-altitude exam pressure. We aren't just talking about basic mechanical arithmetic here. We are talking about the rigorous analytical depth required to execute these operations flawlessly when the clock is ticking down and the pressure is critical. If you've ever sat in that exam hall feeling like you knew the math perfectly, but somehow you still didn't get the marks you expected when results day came around, you were in the exact right place. We are running a full air traffic control exam emergency simulation today to fix exactly that.
So, that brings us to the million-dollar question we have to answer before we clear this airspace. Why do students consistently lose marks on complex numbers? To understand this, I want you to imagine two operators right here in the tower with us. On my left, we have router Alex. Now, Alex is incredibly smart but gets totally bogged down in the minor algebraic details. When a complex division question comes in, Alex starts second-guessing the Cartesian form, overthinks the arithmetic, and ends up in an infinite holding pattern of self-doubt, burning precious time. On my right, we have router Sam. Sam is the opposite. Sam sees the complex numbers, rushes the calculation, totally forgets to multiply by the complex conjugate in the denominator, and tries to clear the argument for landing way too fast without verifying the structural safety regulations of the math. Both Alex and Sam crash their scores. It's a mathematical concept that seems straightforward on the surface, but it's a notorious trap on the 9709 paper. Today, this masterclass is your exclusive look behind the academic curtain. We are decoding the principal examiner reports to reveal exactly what the examiners are looking for so you never leave easy marks on the table again.
Okay, let's initiate the radar grid and dive into our flight plan for today. We'll start by defining the A-star difference, essentially what gets you VIP clearance. Then we'll build our core conceptual foundations. After that, we'll move into practical application with the procedural framework and the crucial method mark strategy. Finally, we'll bring it all home with the top examiner warnings. This structured approach is exactly how you should be actively managing your syllabus, constantly scanning the horizon for these key elements.
Let's transition into Section 1 and establish the primary approach factor. What genuinely separates the top-tier A-star candidates from the rest of the pack when the exam tower is in total chaos?
Remember router Sam from a minute ago? A B-grade candidate operates exactly like Sam. They rely on superficial breadth. They memorize the raw formulas for adding or dividing complex numbers, but they treat them like isolated parlor tricks. They just want to get the plane on the ground, regardless of the wind conditions. The academic benchmarks for Cambridge mathematics, however, heavily prioritize analytical depth over that superficial breadth. An A-star student, and the syllabus explicitly highlights this, possesses a connected conceptual understanding that is completely transferable to unfamiliar contexts. They don't just blindly calculate. They logically structure their reasoning so they can apply complex number operations to entirely new unexpected weather systems on the paper. When Cambridge throws a curveball, the A-star candidates smoothly adjust their vector, because they understand the mechanics of the mathematical airspace, not just the rote steps.
So how do we actually build that elite level of understanding? We need to look at the underlying engineering, the theoretical architecture required to achieve that analytical depth and secure those top marks. The theoretical architecture of complex numbers rests on these four absolute core principles. If we listen in to router Alex and router Sam debating their sequence of operations, it always comes back to these. You need precise definitions, an understanding of causal relationships, evidence-based reasoning, and, listen to me, this is the big one, cross-topic connections. The principal examiner reports highlight a massive, distinct advantage for candidates who reference cross-topic connections during their calculations. Think of cross-topic connections like alternate approach factors. If you can naturally integrate your complex number algebra with your knowledge of trigonometry to find an argument, or coordinate geometry to plot an Argand diagram, you are firing a massive flare gun to the examiner, signaling that you have ultimate A-star mastery of the airspace.
Tower transmission check. Stop what you're doing. Before you clear this response for touchdown, ensure your transponder is fully updated. Subscribe to Ace the Exams right now at @HandleACExams and turn on all your notifications so you never miss a simulation. All right, resuming our vector. We have an urgent alert flashing on the board directly from the examiners. It turns out candidates consistently confuse key terminology and lose incredibly easy marks. Words like modulus, argument, conjugate, you cannot just throw these terms around like casual suggestions. The examiners explicitly state that you should always define or clearly demonstrate your understanding of key terminology before heavily relying on it in your extended mathematical responses. It proves you know exactly which instruments you're using to land the plane. If you don't verify those transponder codes, the examiner has no choice but to ground your answer.
Let's shift our focus from the underlying theory to the actual gritty practice. We are routing the approach vector now, and we need an ironclad procedural framework for systematically processing addition, subtraction, multiplication, and division right there on the exam paper.
Imagine you're mid-flight, and suddenly you encounter an unexpected structural block mid-paragraph, maybe a massive multi-part division question with unknown variables. You need an exact problem-solving rhythm to get back on the glide slope. I call this the deconstruct, solve, evaluate mantra, and it completely mirrors the classic Peel formatting template, but customized for high-level math. Every student should encode this 5-step process into their core memory. Step 1. Identify the given information. What are the known coordinates? Step 2. Break it into logical steps. Step 3. Solve systematically. Execute the algebra flawlessly. Step 4. Check for reasonableness. Look at your answer. Does it actually make sense in the geometric reality of the complex plane? And Step 5. Justify your findings based on the evidence. Don't just leave a number hanging. Link it logically back to the question's core demand.
Building directly on that mantra is the formal, standardized sequence. Extracting data from dense texts and tables, applying the relevant mathematical principles, and executing your analysis with unbelievably clear working are critical professional skills being tested here. This isn't just about getting the right number at the end of the runway. It's about demonstrating a standardized, highly professional approach to problem solving. It's about how you fly the plane. Make absolutely sure you verify your results and always present them in the exact format the tower requested. If they ask for polar form and you give Cartesian, you've landed at the wrong airport.
We are moving into our interactive runway workshop for viewers now. Let's track your live progress. First, I want to give you a highly effective memory hack, because under the severe, pulsing time pressure of an exam, formulas can literally vanish from your mind. To combat this, use a visual story method to deeply encode the concepts. Assessment 1. Imagine a 60-second visual timer on a complex source chart. To isolate the primary trend variable, like finding the modulus and argument, visualize the complex plane as a physical, real-world map. Addition isn't just numbers, it's physically walking a certain path. Multiplication isn't just expanding brackets, it's a dramatic rotation and a stretching of your path. Creating a brief, vivid visual narrative helps your brain retain how to process these numbers under pressure far better than just blank rote memorization.
Speaking of scoring under intense pressure, we need to transition to the marking process itself. How do Cambridge examiners actually allocate their points when reviewing your flight logs? This brings us to the absolutely vital method mark strategy.
All right, time for Assessment 2 in our runway workshop. We're calling this one Debris on the Runway. You have to find the exact line in a sample answer that violates safety regulations and drops points. Here is the massive spotlight fact. Method marks are awarded for the explicit process, not just the final numerical answer. If you mess up a negative sign in line 2 of your complex division, but your underlying method for multiplying the numerator and denominator by the complex conjugate was perfectly structured, you can still salvage major method marks. How you arrive at your destination is just as important as the destination itself. Your working must be incredibly clear, logical, and easy for the examiner to trace. Don't leave debris on the runway by skipping steps. If you make the examiner hunt for your logic, you will lose points. Let's look at the radar and see how this builds across the different tiers of assessment. The framework is fascinating. Low-level responses from students are merely descriptive. They might just state a formula and hope for the best. Mid-level responses are analytical. They actually perform the calculation. But the high-level, A-star responses? They operate on a fully evaluative framework. Higher-order assessment objectives demand that you evaluate alternatives, compare approaches, and provide justified, rock-solid reasoning for your mathematical decisions. In the control tower of this exam, you aren't just a basic calculator crunching data. You are a top-tier mathematical analyst directing traffic. We are entering the final approach now. This is the most critical part of this simulation. We are shifting into an urgent, cautionary tone as we unpack the specific crash data straight from the Cambridge Principal Examiner reports.
Treat these as blaring amber warning lights on your console to dodge on exam day. Here are the top 3 critical traps students fall into. Number 1. Answers are far too vague. You skip steps assuming the examiner knows what you meant. They won't give you the benefit of the doubt. Number 2. Students entirely forget to check their final format and presentation. This is like perfectly lining up the runway and forgetting to lower the landing gear. And number 3. Answers are not specific to the given context of the question. You absolutely must factor in the fuel to mark budget formula. If a question is worth 2 marks and you are spending 12 minutes writing out a massive geometric proof, you are burning way too much fuel for the payload. You have to tailor your final output perfectly to exactly what the prompt demanded, nothing more, nothing less.
Let's log this successful full-mark landing sequence with a direct quote from the Principal Examiner report. Answers on 3.9 complex numbers are often too vague. Examiners want specific details. So the crucial takeaway here is that you simply cannot hide behind messy algebra or incomplete, rushed statements. The examiners have authoritative weight, and they are practically begging you to provide clear, step-by-step specific details and robust evidence in your working. Showing your exact vector every step of the way is exactly how you secure those A-star method marks.
I want to leave you with this final provocative thought as we close out today's simulation. Look back at your own practice papers right now and ask yourself honestly, is your mathematical reasoning clear enough to secure that final A-star touchdown? Or are you just blindly hunting for the final answer, hoping for the best? Remember, the explicit process is the prize. Evaluate your own exam strategy, implement the strict procedural frameworks we mapped out today, and always prioritize analytical depth. Keep running those past paper drills. And before you log off from the tower, subscribe to Ace the Exams, enable that notification bell, and leave a comment down below sharing exactly which Cambridge paper gives you the absolute most exam anxiety. We will see you in the next masterclass.